And we're wrapping up this chapter. We're on the very last thing that we're looking at, and that's two-sample t-tests. This is fine. It usually goes pretty well, with one kind of little exception, and that is that it's very common for students to mix up matched pairs t-tests with two-sample t-tests. And it's pretty easy to tell them apart, but having said that, it still happens that people mix it up. Anyway, the matched pairs, we had one sample. We measured everyone in the sample twice. We took the difference, and so we did a one sample t-test. It's not going to be the same thing for two sample. For two sample, we're going to compare two means from two different populations. Like, say I have 80 men and I'm measuring them for some criteria, and I get the average, and then I get another group of 80 women, and or maybe let's say 60. Let's make the sample sizes different because that we can do that. Let's just say those 60 women, I get measurements from all of them for a certain criteria and get an average. So I got an average for that criteria for men, an average for women. I compare the two to see if they're reasonably the same or if they seem to be different. All right. So that's a lot different from a matched pairs. There is no pairing in two sample T procedures. All right. There's no getting two readings from one person. There's no one person in one group paired up with one person of another group. Doesn't work that way. You can tell when you have a two-sample t-test because your sample sizes may not be equal. Now, they might be equal, but in most cases they aren't, and that's okay. So the goal of inference is to compare the responses to treatments or to compare the characteristics from two populations. This is not matched pairs, right? It's very common for people to do matched pairs as a two-sample t-test. Excuse me. It's a lot less possible to do it the other way, to do a two-sample as a matched pairs. All right, so in a matched pairs, we have one subject that's measured twice. Well, each subject is measured twice. In a two-sample, we have two groups where everybody's measured once, and we get two means and compare them. So you can see for matched pairs, it's just one mean. Mu of a difference is 0. Here, mu1 equals mu2. That would be your HO statement for each of those things. You always have equal number sets in matched pairs because you have to measure everyone twice. So if you have 10 individuals, then you have 10 readings for before intervention and 10 readings for after, 10 and 10. In two samples, they're mostly unequal. They can be equal, but it's sort of rare. All right, the assumptions are pretty much the same. All right, you need two simple random samples because you have two populations that we're going to sample from. The samples have to be independent, no shared subjects. Now the third one you don't have to list. The same variable is measured for both samples. Duh, of course they are. You couldn't do inference if they were different variables, so don't list that one. Both populations are normally distributed. All right, so you can look at sample size for both samples, and if they're over 30, you're good to go. But remember that when you finally are doing your inference, you're actually doing it in one sampling distribution. Think back to when we did random variables, and we had random variable x that was normally distributed and random variable y that was normally distributed. We either added or subtracted them and got a third random variable z that was also normally distributed. All right, so we're blending two independent populations into one that same way. All right, and then for the last one, populations are at least 10 times their sample sizes. Note the plural. So you have a plural for this one and you have a plural for this one. Here we're going to just say normality of the sampling distribution, which is made from two populations. Okay, sorry about all of the graphics here. All right, Yeah, so for HO, mu1 equals mu2, or you can list it as mu1 minus mu2 equals 0. So this is based on a difference, right? So if you look at what I have here, that doesn't look like it's based on a difference, but it's usually what I pick, along with this alternative, which is just this one with the equal to replaced with inequalities. Or you can do it this way, either way. But be careful with your directional, like so, because you can get those backwards just like with matched pairs. And on our last quiz, I had a number of kids that got really, really high p-values. That's the key. You're not supposed to get really high p-values. If you're getting them, then you're getting the complement of the p-value that you want. All right, so be careful on your one-sided tests. If you get a high p-value, check the order of your subtraction. All right, here's your test statistic. I still have a few people that are trying like crazy to do everything with formulas. You can stop that now, all right, because this is complicated. And if you look at this, this is actually not part of the final formulas, because it's just assumed from HO that mu1 minus mu2 equals 0. So it's really just x bar 1 minus x bar 2 divided by the standard error. All right, your degrees of freedom are n1 minus 1 or n2 minus 1, whichever is the smallest, but just let the calculator figure it out for you. And let me show you why. All right, so let me get the packet here. Let's see, here it is. All right, this is, I think, page 13 in your packet, but if you look at this formula right here, see this nasty formula I just kind of made blue? That's how your calculator will determine degrees of freedom. Now your n1 minus 1 or n2 minus 1 is just a conservative estimate. This is the exact, and nobody uses it. Don't use it, all right? It's not even in your formula chart. So it would take you another 10 minutes of work time to get this. The whole thing pops up on your calculator when you do your inference. Just use it, okay? Just don't mess with that. It's just crazy. It's not what we need. All right, so let's get back to this. You can do n1 minus 1 or n2 minus 1 and use that, but just let the calculator handle it for you. Okay, confidence intervals. Here's your sample estimate, plus or minus margin of error, and after the t-star you have your standard error right there. And you can see that this is also based on a difference. So look, the only reason to do a confidence interval for two samples is the same as the only reason that we did it for matched pairs, is to look for 0. So again, your degrees of freedom, they'll just come up in the calculator, but look for 0. No difference in the interval. Always do that. If 0 is there, there's evidence that there's no difference between whatever your two populations are. If 0 isn't in there, and you know the order which you subtracted, then there is evidence that they aren't the same, and based on the order of your subtraction, you can figure out which one is more. All right, so there's your assignment. What I'm going to do now is just close this out, and I'm going to go ahead and just post up the work that we did in class. That would be this. And I'm not drawing it out for you. I'll have it up here where you can pause it and you can just copy it down. So here it is, article so close yet so far, predictors of attrition in college seniors. Attrition is dropping out. It's like who's left after people leave. It attempts to describe differences between college seniors who disenroll, a nice way to say drop out, before graduating and those who graduate. Researchers randomly selected 42 non-returning and 48 graduating seniors. Okay, you see how these are independent? And you also notice that the 42 and 48 are not the same. There's no way this could ever be matched pairs. All right, none of whom were transfer students. These 90 students rated themselves on personal contact. Personal contact is, you know, how many people you know on campus or you've met while attending school. And campus involvement is a way to just rate people for clubs that they've joined, or, if you're going to join up with young Republicans or young Democrats or whatever, how you got involved with extracurriculars on campus. So here's the data. And so it's a mishmash. The top the top organizer is for returning, the bottom is for non-returning, and they're both split by personal contact and campus involvement. So the first thing we're going to do is to construct a 95% confidence interval for the difference in the mean campus involvement rating. See how I put check marks there so I knew what I was going for? And for returning and non-returning students, does your interval support the statement that students who do not return are less involved on average than those that do? All right, so here is your write-up. You have to define mu1 and mu2. I'm going to put the returning in my calculator first, the non-returning in second, so that's the order of my subtraction, non-returning subtracted from returning. So I define mu1 as the mean for campus involvement for returning students, and mu2 is the mean for campus involvement for non. And my assumptions were met. SRS and independent for both samples was given. The populations are both at least 10 times the sample size. That is probably true. I don't know that it is for a fact, but you know what? I've talked to other teachers in the district, and they just say, look, unless you have a compelling reason to doubt that, just write it down and it's fine. And then we've got big enough sample sizes for the central limit theorem. So normality of your sampling distribution, singular, is approximated by sample size. So I listed it, can't argue with that. Be really careful how you define or how you state what procedure you're doing, because on the quiz it was all over the map. These are results for a 2-sample t interval for means. And now we're ready to just generate these numbers. So I'm going to call this up, and I'm going to work off of the scratch pad. You can go down here if you want. It doesn't matter. In fact, I'll do it there. So menu, statistics, confidence intervals, and let's see, 2-sample t interval, choice 4. All right, we didn't store anything in any list. So we're not doing data, we're doing stats. That's what's in the table. So tab to OK, and now we have to enter these things. All right. So for the returning, the average for campus involvement was 3.21. Whoops. 3.21 with a standard deviation of 1.01. N1 was 48, and X bar 2 was for the non-returning, that's 3.31, and the standard deviation on that was 1.03, and N2 is 42. It's okay to have different sample sizes. Tab down, we do want a 95% confidence interval, so we don't need to change that. Now tab again, this is new. Pooled, yes or no? Stay with no. What pooling is an assumption of equal variance between your populations, and we don't know that. And it's a little bit beyond what we are needing to do. So let's just tab to OK and leave that on no. Note that to yourself if you need to. Okay. So here's your lower limit, upper limit. Don't write it with this terminology. Write it like this. All right, C95, and there are your two numbers. And I believe we had degrees of freedom here that we can just copy down, see, right there. So we're going to use that, and that's where I got it. So give the usual spiel. We are 95% confident that the true mean difference in the means for returning and non-returning students for campus involvement rating, wow, falls in the interval from negative 0.5287 to 0.32873. If it had been any other interval practically, we would not be continuing, but we need to look for 0, and 0 is there. See negative quantity here, positive here. So since 0 is in the interval, there may not be a difference between the two groups at a 95% confidence level. All right, so I'm going to leave this up here, and you're going to pause, all right? And then I'm going to move on after you're done copying this down. So pause. All right, I'm assuming you're done pausing, so I'm going to go on to the next page. And the next page is, do students who don't return have a lower personal contact rating than those who do return? So that's directional, one more than the other. Test the relevant hypothesis using a significance level of 0.01. All right, so here we go. mu1 is the true mean personal contact rating for returning students, and mu2 is the same for non-returning. HO is that the two averages are the same, right? No difference, no change, no effect. That's HO for you. Now, since they're asking if those that don't return are lower, they're implying that maybe those that do return are higher. So that would be mu1 is greater than mu2. All right? So now I'm going to be honest with you. What we did in class, since we already checked assumptions in problem number 1, and these two are just one is linked to the other, I went ahead and just wrote here, assumptions previously verified in problem 1. And I didn't write this all out, but basically it's up to you if you want to. But just so long as they really were checked in an earlier version of the problem, then you're gold. All right. So this is results for a 2-sample t-test for means, and we're doing those things that we did not check. All right, so let's just scoot down and get to an open field, and we'll do menu, statistics, and stat tests, and a 2-sample t-test, choice 4. We're doing stats again, and let's hit OK. All right, so personal contact for those returning, 3.22. Standard deviation is 0.93. And I think, no, I don't have a typo. I'm good. So that's 48. And then X bar 2 is 2.41. That looks kind of different. And standard deviation is 1.03. And sample size for that group is 42. Now we want to do less than. So hit the right arrow and go up and choose, I'm sorry, not less than, we want greater than. All right, so HA alternative is that mu1 is greater than mu2. And we're going to get to that pooled thing again, just leave it on no and hit enter. All right, so these are the things that we need to record: the t value, the p value, and the degrees of freedom. All right, you might throw the alpha in there too. All right, so after you write t is 3.89359, I want you to just think about that number. And isn't that really saying that your sample estimate is like almost 4 standard deviations above the mean, which I believe it is. So that should give you an incredibly small p-value, 4 zeros and 2 nines. Yeah, that's pretty small. There's your degrees of freedom, and there's your alpha. And the usual thing, since p is less than alpha, the results are significant. We reject HO. That's a tiny p-value. So we have strong evidence that returning students may have a higher mean personal contact rating than non-returning students. So there it is. We're done. All right, so let me scoot this up and hit pause. Yeah, I guess that'll all fit. And you can copy that down, and these will serve as a template for your homework.